We started learning about the definite integral last time. The definite integral in the context of physics applications. Let's think about the definite integral in a more abstract sense as just a mathematical concept. We used t as the independent variable last week because it represented time. But now when I'm not focused on an application, I'm going to use the more typical independent variable. I'm going to use an x. In reality, it doesn't matter what letter you use. It's just sort of habit what we end up using. It's convenience. The symbol for the definite integral is, well, an integral sign. And then you have a lower limit of integration, call it A, and an upper limit of integration, call it B. So this is this curvy S, elongated curvy S is called integral sign. And, oops, not psi, but sine. There's an N there. The number down here is called the lower limit of integration. It doesn't mean it's calculated as a limit, okay? When I say lower limit of integration, it's just the number on the bottom of the integral sign. Or if you're thinking of the integral on a number line, it's the left endpoint. Lower limit of integration. And the B is the upper limit of integration. Upper limit of integration. Then you write the function that you are integrating to the right of the integral sign, f of x, say. And then it's like you're re-emphasizing what the variable is by writing dx, kind of reminiscent of Leibniz notation with derivatives when we write dy dx. We're emphasizing the variable that we are integrating with respect to is x when I write dx. Well, you might say, well, what other variable is there? There's only an x there. Well, I mean, if we were doing multivariable calculus, there could be another variable there, or there could be a parameter if we were thinking about a family of functions. So it is good to emphasize what the other variable is. And Leibniz, when he created this notation, was thinking about giving a more physical meaning to dx. It does even have a name or even a couple of names, which I'll mention in a minute. F of x is the function you're integrating. That's called the integrand. Integrand is the function being integrated. Dx, a couple different names people use here. Probably the most common name in a calculus course is to call this a differential. But Leibniz also thought of it as what you might say is an infinitesimal or infinitesimal. What does infinitesimal mean? I can't give a rigorous definition without doing graduate level math. And the definition, well, the pseudo definition I'm about to give you actually is nonsense. Okay, it's a convenient fiction. You can think of dx and infinitesimal as being, well, you could say it's a positive number that's smaller than any other positive number, positive real number. But wait a minute, there is no such thing. There's no such thing as a positive number that's smaller than any other positive number. There's no smallest positive real number. If you think it's 0.00001, you're wrong, because I can add another zero. If you think it's 10 to the negative billion power, you're wrong, because I could do 10 to the negative trillion power. In fact, I mean, simpler than that, you could always take any positive number and divide it by 2 and get another smaller positive number. Or you could square it, if it's close enough to 0 at least, and get another smaller positive number. So to call this a positive number smaller than any other real positive number is actually a nonsense statement. But it's convenient to imagine it that way. Okay? Use your imaginations. This is what scientists and engineers do in this context, is they use their imagination. They may think they're doing rigorous math, but they're not. Okay, but it is still convenient, and it's even helpful. It's even helpful to imagine it that way, though it may not be clear how yet. That'll be more clear on Wednesday, I think. What does it represent? Well, if the graph of f is always above the horizontal axis, it represents the area under the curve over that interval from A to B. More generally, if the graph goes both above and below the axis, say it's above here, below here, then goes back above there. Well, let's go back below and above one more time. Let's say this is A and this is B. If I label each of these regions with areas, call this area A1. That's this area A2. And when I'm labeling these areas, I am thinking of these areas in the ordinary way as positive areas. All these A's represent positive quantities. The definite integral is going to then be the sum of the areas that are below the graph and above the axis when the graph is above the axis, minus, I said minus the sum of the areas when the graph is below the axis that are above the graph but still below the axis. That's kind of a mouthful. It's going to be A1 plus A3 plus A5 minus A2 plus A4 for this particular picture. Okay, if it was a different picture, then it would be a different formula. Say it again. It's the sum of areas under the graph and above the axis when the graph is above the axis, minus the sum of the areas above the graph and below the axis when the graph is below the axis. And yes, you can distribute the minus sign through here. This is the same as A1 plus A3 plus A5 minus A2 minus A4. It does equal that when you distribute the minus sign through. But this just begs a question. And in fact, it begs more than one question. One question it begs is like, well, how do you find these A's? How do you find these areas? I mean, you could eyeball it and try to guess, right? If you had scales on the axes, both the horizontal and vertical axis, maybe you could make a bunch of little boxes, a bunch of little rectangles like we talked about a week ago, and estimate the areas. We will do that today. And then you have to ask, well, that's just an approximation. How do I find the areas exactly? We will see today, as we saw a week ago, that it's really a limiting process. The limit concept is inescapable in calculus. It is, in essence, what separates calculus from plain old algebra, is the limit concept, both with derivatives and with integrals, and in calculus 2 with infinite series, which are infinite sums, adding up infinitely many numbers. Did I say that? Yes, I said add up infinitely many numbers. Maybe you've done it before with geometric series. If you think about it, how can anybody possibly add up infinitely many numbers? Doesn't that sound like an impossible task? It technically is impossible, but we can define it in such a way that it still makes sense and it's still useful. It's a convenient fiction again. Pretend that you can add up infinitely many numbers. And when I say that, I am serious. That is what we're doing. We're pretending we add up infinitely many numbers. The amazing thing is that we can do that, and it makes sense, and it's useful. Okay? It should also beg another question, if you think about it longer. How do you know there even is an area? Wait a minute. Is that a valid question? I mean, duh, can't you just look at it? Obviously there's an area. Well, it's actually not so obvious. In fact, there are some weird functions where the area under the graph does not exist. You cannot define an area under the graph of some functions. Maybe I'll even show you some functions like that, just not today. So it's really more than just saying it equals this. You really also have to define what area even means. Now, volume can be defined relatively easy in science, because what you can say is, oh, what's the volume of this object? Well, get a bathtub, right? Fill it with water and drop it in and figure out how much water gets displaced. There, that's the answer. That's the volume. But how do you do that with area? What do you need? Like just a two-dimensional bathtub instead of 3 dimensions? But is there such a thing? Yeah, kind of, but we don't go into that in a math class.